In this video, we're going to look at something called the trapezoidal rule. The idea of what we're doing in this video is we want to find a way to approximate a definite integral. So imagine you've got the integral from a to b of some function f of x dx. Sometimes these integrals are hard or impossible to calculate, and so we want to come up with a numerical method to help us approximate the value. Geometrically, what we're doing when we're working with a definite integral is we're trying to find the area under the curve, y equal f of x, between the x values a and b. So that's what we're trying to approximate. Let's break into a new page and we'll see how the trapezoidal rule works. So we're talking about the area under a curve over a certain section of the x-axis. So let's say this is x equal a, x equal b here, and we're trying to approximate this area under the curve. So what we're going to do is divide our area into n intervals, and we're going to approximate the area by trapezoids. So a trapezoid is sort of like a rectangle, except the heights on the two sides are different. So a trapezoid looks something like that. All right, so let's look at this section of the x-axis. We're just going to divide this into n intervals. So we'll go through some examples in a few minutes. N could be something like 4 or 5, depending on the problem. So just imagine dividing that up into n intervals. And then over each of those little intervals, let's look at our area and let's find the trapezoid determined by these 2 points that lie on the curve. So for any interval, let's look at this one here. There's going to be a point where we hit the curve, another point where we hit the curve, and then just forming a straight line segment between those two creates a trapezoid. So you're going to do that for each of these little intervals all the way across the area. So let's talk about a few quantities we're going to need to approximate the area. First of all, we could think about the length, or you could say the base of each of these trapezoids. Well, our total interval from a to b has length b minus a. And if we then divide that into n parts, then each of these little bases here is b minus a over n. So that's one quantity we're going to need. Every trapezoid in this picture has that same base. The other quantity we're going to need is we're going to need to talk about the heights of these trapezoids. So this left height here, the leftmost height, let's call that y0. And then as we work our way across these different points on the curve, let's call this y1, and then y2, etc. So by the time we get to the rightmost y value here, that will be yn. So the trapezoid on the far right will have y values, let's say y sub n minus 1 and y sub n. So let's focus in on just this trapezoid, the one that's sitting furthest to the right, and let's see if we can figure out the area of that trapezoid. So let's think about this. The area of a rectangle is base times height. The area of a trapezoid is a little different. It's the base times the average height. And if we think about what the average height would be for this rightmost trapezoid here, you would just take the average of your two heights. So you'd go y sub n minus 1 plus y sub n and just divide by 2. So that gives you the average height of the trapezoid. I'll show that on this trapezoid on the right here. So if you could figure out the average height of that trapezoid, maybe about there, then you're basically saying, okay, the area of that rectangle using the average height is the same as the area of the trapezoids. So let's see if we can clean up this formula a little bit. We've said that the base is going to have length b minus a over n. So we've got b minus a over n times y sub n minus 1 plus y sub n all over 2. And what we'll typically do is just bring that over 2 out in front and make it b minus a over 2n times y sub n minus 1 plus y sub n. So let's say our approximate area under our curve is what we get if we sum up the areas of all these trapezoids. So let's think about the leftmost trapezoid, the one that's sitting over here. So its heights are called y0 and y1. Therefore, its area is going to be b minus a over 2n times y0 plus y1. And then we could do the same thing for the second trapezoid. So that would look like b minus a over 2n. Its heights would be y1 and y2. so y1 plus y2. And you could do that all the way across. As we said, the trapezoid on the far right would look like b minus a over 2n times y sub n minus 1 plus y sub n. So the idea here, to come up with a nice looking formula, we're going to have basically our final formula in the next step. You would factor out the b minus a over 2n, and then what you'd have in the brackets is something that looks like y0 plus y1 plus y1 plus y2, and you do that all the way across. You get y sub n minus 1 plus y sub n at the back. And then the idea is that all of these terms in the middle are going to be doubled up. You're going to have two y1s. You're going to have two y2s. And as we work our way across the second last term, you're going to have two y sub n minus 1s. So all of these y's are going to have coefficient 2, except for the very first one and the very last one. So let's write down our trapezoidal rule. It says if you want to approximate the value of a definite integral, you're going to say it's approximately b minus a over 2n. The n value will be given in the question. And then inside the brackets, you have y0 plus 2y1 plus 2y2. All these coefficients here all the way across are 2, except for the first and last terms. So your second last term would look like 2 times y sub n minus 1, and then finally plus y sub n. So there's our trapezoidal rule, and we spent just a little bit of time drawing the picture, doing a bit of algebra to understand where that comes from. Bottom line is that you're approximating the area under the curve, which is this stuff, by the sum of areas of a bunch of trapezoids, which is this stuff. Here's our first example. We're going to approximate a certain integral using the trapezoidal rule with 4 intervals, and we want to give our answer to 4 decimal places. The integral that we want to try to approximate is this integral here. So first thing I would do is I would write down what our number of intervals is. N is that number of intervals, and we're told in the question that's going to be 4. Next thing we're going to do is we're going to make a table of values. So we need to figure out some x and y values for the points that are forming the edge of our trapezoids. When we think about the different x values that we're going to be working with, I'm going to draw a picture here. You want to be starting at A, finishing at B, and then you're just going up in little increments of b minus a over n. So let's say for this problem here, we want to start at 2. So starting at whatever the smallest number is on the integral, and you're finishing at whatever the top number is. So end at 3. And we're going to go up by increments of whatever b minus a over n is. So that's usually something that you want to calculate towards the beginning of the problem. Okay, so b minus a, be 3 minus 2, divide that by n. That gives us 1/4, or if we do this in decimal, let's call this 0.25. Okay, so we go up in steps of 0.25. And that's just like saying this point here, or this x value here is 2, and we're just going to work our way across in increments of 0.25. So we'll go 2, 2.25, 2.5, etc., all the way to 3. And those are just marking off the edges of our trapezoids. So let's fill those numbers in to our little table here. So I put our n value over on the side. I put our b minus a over n just over on the side to make a bit more room for this table. So we're starting at 2, ending at 3, and going up in increments of 0.25. Now we're going to work on putting some y values into the table. And the y values that you use, let's look back to our integral here, and let's just think about what our function is that we're trying to integrate. It's 1 over x. So the y values we're going to be plugging in, 1 over x. And as we build the numbers in this column, what we're doing is we're figuring out the y values of the points sitting over these different parts of the x-axis. So that's going to give us the heights of all our different trapezoids as we move our way across here. So let's try plugging in. So if we take our x equal 2, plug it into 1 over x, we get 0.5. If we take x equal 2.25, plug it in, we're going to get 0.4. Repeating. And this is where we can think about how many decimal places we need to write down. So let's scroll back to the original problem here. It said, give your answer to 4 decimal places. So we're going to use the general rule of thumb here that you're going to carry 2 extra decimal places throughout your calculation. So if you want your final answer to 4 decimal places, let's carry 6 in the y values here. And we'll do the same thing, just plug in all the way down this table with our different x values plugging into 1 over x. So our y values will look like 0.4, then 0.36 repeating, and then finally 0.3 repeating. So now we're ready to do the final stage of our calculation where we put this all together using our formula. So let's write down what we're trying to do. We're trying to approximate the integral from 2 to 3 of 1 over x dx. According to our trapezoidal rule, that's going to be approximately b minus a over 2n times y0 plus 2y1 plus 2y2 plus 2y3 plus y4. So notice that if you have 4 intervals, you're actually going to have 5 different y values in your table. Your first y value will always be called y0, and your last y value will always be called yn. So here n is 4, so our last y value is y4. All these middle y values get multiplied by 2, and the first and last ones just have coefficient 1. So we've almost got everything we need to plug in here. The only thing we should think about in a little bit more detail is this number here. So this guy is b minus a over n, which is a number that we've already calculated, times another factor of a half. So let's just be aware that there's that extra factor of 2 that came out in the denominator when we simplified this expression. So let's scroll back up to the beginning of the problem where we set things up. Remember, we said b minus a over n is equal to 0.25. So that's the size of the step that we're taking as we move across the x-axis. Now, when we do our final calculation, we're not just taking that 0.25, it's actually 0.25 over 2, because there's that factor of 2 that came out in the denominator when we simplified. So that's just something to be aware of. And with that, I think we're ready to plug in and get our answer. So it's going to look like 0.25 over 2 times our brackets. So I'm going to spell out all the details here just so we're clear, just because this is our first time doing the problem. So we're going to have y0, which is 0.5. Then we're going to have plus 2 times, well, since all 3 of these middle terms are going to be multiplied by 2, I might just pull the 2 out like that. So we have to take 0.4 repeating plus 0.4 plus 0.36 repeating. So those are all getting multiplied by 2. And then the last one has coefficient 1. And we've carried everything to 6 decimal places. So you can try putting that into your calculator. Final answer to 4 decimal places comes out to approximately 0.4062. So that's a good estimate for what this definite integral is equal to. Now you might wonder what happens as we change our n value. So as the number of intervals goes to infinity, or you could say as the number of intervals gets bigger, the approximation gets better and better. So this approximate value that we've calculated approaches the true value of the integral. In other words, if you do the approximation with 100 intervals, it's going to be more work, but it's going to give you a truer value than if you did the approximation with 4 intervals. So let's try one more problem. Make sure that we've got this trapezoidal rule down. So let's approximate using the trapezoidal rule with 5 intervals. Our answer is going to be given to 2 decimal places. And here's the integral that we want to approximate. It's the integral from 0 to 2 of 3 to the x dx. So first thing would be to point out what n is. That's our number of intervals. So that's going to be 5. And the other thing we need is b minus a over n. B and A are the numbers on the integral. B is the big number. So you go 2 minus 0 over 5. That's going to give us 0.4. So that's the size of the step that we're taking as we move across the x-axis. From there, we should be able to build a table of values. So now that we've seen this once before, we should be able to do this part more quickly. So you start at your small number, a, finish at your big number, b, and you're going up in steps of 0.4. So whatever your b minus a over n value is, that's how much you increment x by. So our x values will be 0, 0.4, 0.8, 1.2, 1.6, and 2, just going up in increments of 0.4. Then, to get our y values, we plug into whatever function we're trying to integrate. So the function we're trying to integrate here is 3 to the x. All right, so let's write that down and we can plug in. So 3 to the 0 is 1. For something like 3 to the 0.4, I would say it's fast enough just to write 3 to the 0.4. That'll be fine to type into our calculator. So we'll just go 3 to the appropriate value until we get to the bottom row, and then 3 squared, we can call that 9. And then once you've got that table built, then we can actually write down our trapezoidal rule. So we can say the integral from 0 to 2 of 3 to the x dx, according to our rule, it's going to be approximately b minus a over 2n times y0 plus 2y1 plus 2y2. If you want, you can think about what the last number is going to be. It's going to be yn, and in this problem, n is 5. So our last y value is going to be y5. Our second last one would look like 2y4. So I think the one thing to watch out for in terms of plugging in is that this number here is going to be your b minus a over n that you've already calculated, but divided by 2. So we've already figured out that b minus a over n is 0.4. In other words, the number we want out in front is 0.4 divided by 2. So let's call that 0.2. If you want to think of this on a more intuitive level, the reason why you have to divide b minus a over n by 2 is basically because most of these coefficients are being doubled in here. So the doubling that's happening in here is balancing out with the factor of 2 that we've got in the denominator. That's a nice sort of gut check, I guess, way of thinking about it. Okay, and then we plug in our y values. First and last ones stay as they are, but all the middle ones get doubled. So we've got 2 times a bunch of stuff, and for the sake of typing that into your calculator, you could actually pull the 2 out and then just write all the stuff that's doubling in brackets. So 3 to the 0.4 plus 3 to the 0.8 plus 3 to the 1.2 plus 3 to the 1.6. And that way, this is relatively efficient to type into our calculator. Then, plugging into the calculator and remembering that we want our final answer to 2 decimal places comes out to about 7.40. So that is the trapezoidal rule for approximating integrals. Thanks for watching.